This video is going to talk about how to approach the take-home test and hopefully give you a little bit of guidance and maybe some tips and tricks on how to do your unknowns. So I'm going to share my screen here. I have two unknowns I'm going to go through. The first one is unknown number 30. And so open on my screen here, I have the actual unknown, and I have the blank test page, which is posted up on Canvas. So the very first thing that I'm going to do is I'm going to use the elemental analysis data that is listed right here, and I'm going to turn that into a chemical formula. So I'm actually going to make this screen a little bit larger here. And we're told that carbon is 54.53 and hydrogen is 9.15, oxygen 36.32. So those are percentages, but really we're just going to call them grams. And so these are my percentages that I've just have said they're grams. We're going to convert those into moles by dividing by molar masses. So I get 4.5, and our goal here is to end up with whole numbers. So I am putting 1 decimal place, but we don't need to put a lot of decimal places. I'm going to go back and add 1 to my carbon up there. Our next step is to divide them all by the smallest. And this will get them into a nicer ratio. So the carbon is our smallest. Oh, I'm sorry, oxygen's our smallest. So divided by 2.27. So oxygen is 1. Carbon is 2. And for hydrogen, I get 3.99, so I'm going to round that to 4. So what I end up with is C2H4O. This is our empirical formula, and so we want to compare that to our other data. And on my mass spec right here, I can see that my molecular ion has a mass of 88, and that is the molar mass of the molecular compound, and so I need to compare that to the molar mass of my empirical. So my molar mass of my empirical, I'm going to add that up real quick, is 44. So to turn our empirical formula into a molecular, I'm going to take that 88 from the mass spec, divide it by the 44, and I get 2. And so that means that my empirical formula is twice as big as my empirical. So I'm going to have C4H8O2. So I know that that's my formula I have to work with. So I'm just going to rewrite that over here. Another thing that we can check just to make sure that it matches is within our hydrogen NMR, we have our integration numbers. So 6, 7, 8, so that matches. Let me erase those for right now. And then in our carbon data, we have 4 carbons listed, and that matches. So that tells me that it essentially tells me that we're correct. Okay, so we're going to look at the hydrogen data next. I'm going to share both screens here. So I'm going to fill these tables out as we go through this. This is number 30. For the hydrogen data, to fill in the table, I'm looking at the middle of any peaks. Okay, thank you. And so right here. So that's 1.2 for that first peak. And the multiplicity of that first peak is a triplet because it contains the 3 peaks. And the number of hydrogens is 3. And so I know it's a triplet because of the shape, and I know it contains 3 hydrogens because it literally tells me right there. For the next one, it's right at, looks like we're right at 2.4. And that is a singlet, and again 3 hydrogens. And then that last one, looks like we're right at 3.7. And that is a quartet and 2 hydrogens. So just from this information, I know that I have, let's see, I'm going to go over here. I know that I have a methyl. I know that I have another methyl. And I know that I have a CH2. We know that there are also 2 oxygens in this formula. Oh, one thing we didn't do, we didn't calculate our degrees of unsaturation. So let's do that real quick. Our formula is 2 carbons plus 2 plus the nitrogens minus the hydrogens minus the halogens, all divided by 2. So for this one, that's 2 times 4 plus the 2 minus 8. So that's 10 minus 8. So 2 over 2. So it has 1 degree of unsaturation. And we have 2 oxygens in there and only 4 hydrogens. So this is telling me that it's probably a pi bond and it's probably some type of carbonyl. And we can look in the IR in a little bit to get some confirmation on that. But just based off of how many carbons and oxygens we have and 1 degree of unsaturation, that's probably a good indication. So let me go back to our NMR here. The methyl group that is a singlet is going to be isolated from everybody else. So if we do have a carbonyl, this could be right next to the carbonyl and at the end of the chain. The other 2 are going to be next to each other because a triplet tells us that it needs to have 2 neighbors, and a quartet tells us that it needs to have 3 neighbors. So essentially I know that I have 2 puzzle pieces so far. I have a CH3 that's by itself, and I have a CH2 CH3 that have to be next to each other. When we look at the carbon data, and I'm going to put this into our table, so right here, 171.0, and the multiplicity is a singlet. We have 59.2 triplet, 17.3 quartet, and 13.6 quartet. When we compare that data to what we've already figured out, this would be a quartet, this would be a quartet, this would be a triplet, so the only peak that would be left would be a carbon that is bonded to an oxygen. So just based off of our carbon and hydrogen NMR, we have a lot of the puzzle pieces for our structure. That would be our singlet. So my next stop then is to go look at the IR. And I'm going to do my half screen again here. So as I look at my IR, I want to assign every peak that is 1500 or larger. So when I look at my IR over here, I have a pretty big peak at about 2900, and you're going to see one there in almost everything because this is just sp3 carbon hydrogen bonds. And then there's also this large peak that is at about 17 30 or so. So this is definitely in the carbonyl region, and when you look in Technique 25 in your lab book, it has some tables, and so specifically at 1730, this is a carbonyl for an ester. And then I'm also going to add over here that peak at 2900, we're going to label it as strong. And that peak at 1730, I'm also going to label that one as strong. And that's all I'm going to label. So the IR does also give us information about peaks that we don't see. And what I mean by that is we don't have an alcohol peak or a carboxylic acid peak over here. So that essentially means we have to have an ester based off of the other information we know. So my IR table is actually done. So based off of that information, I'm going to go back and finish my structure. So we know it has these pieces over here. We know it also is going to have that single bonded oxygen. And so really there's only a couple ways to put this together. We can say CH3O CH2CH3, or we can put that oxygen on the other side. And so the way that we're going to decide which one is correct is we're going to go back and look at our NMR. And the peak that has the highest chemical shift is that CH2 group. I just realized I put a 3 here instead of a 2. So that tells me that this structure is my correct structure because my oxygen is next to that CH2 group. So I'm going to just go across this and label this as A, B, C, and D. And then I'm going to go back to my tables and fill in those missing assignments. So on my hydrogen NMR, the CH2 is letter C. I have 2 methyl groups, but the one that's a singlet is letter A, and the one that's a triplet is letter D. And then in my carbon NMR, the singlet is B, it's that carbonyl carbon. The triplet is C, the CH2, and then I have 2 quartets. The one with the higher chemical shift, though, would be the one that's closer to the oxygen. So it would be letter A, and then our last one would be letter D. So our IR table is done, our hydrogen NMR table is done, and our carbon NMR table is done. So that means we have our mass spec table left. So there's only 4 labeled peaks. So we have 88, 70, 61, and 43. I'm going to label the peak at 88 as my molecular ion peak, and then for the rest of them I can just say M minus and then whatever the difference is. So 88 minus 70 is 18. 88 minus 61 is 27. Oops, there we go. And 88 minus 43 is 45. The cation fragment is whatever made the M over Z peak. So for the first one, it's literally just the entire molecule. So I'm just going to put another M there, and then nothing broke off of it, so we're just going to put little dashes. For the next one, we know that it lost 18. A really common thing that breaks off from losing 18 is a water molecule. So the 18 is water, and the piece that was left behind, if an ester loses water, that means there had to be some kind of rearrangement. So I'm just going to put the remainder of the chemical formula here. 27 is a ethyl group. So 2 carbons is or an ethene group, excuse me. So we're going to put CH2, CH2 over here, and then the rest of the molecule would be the rest of the ester. So the CH3, C, double bonded to the oxygen, and then what's left behind is it actually would make a carboxylic acid. So this is really just the rest of the pieces. And then over here, the piece that would weigh 45, the piece that breaks off, is the oxygen with the carbons. And what's left behind is the rest of our molecule. So as you're trying to decide that, let me get our molecule on the screen over here, you're kind of looking at all the different ways that it can break. So we are saying, well, if we break the bond here, it would lose this much weight. If we break the bond here, it would lose this much weight. And the piece that's breaking off that we're not getting detected is the radical, so that's the amount that's being subtracted by, and the piece that is being detected is the cation piece. And for that mass spec, we only need to write down the ones that are labeled. I am missing one label here though. Peak number 43 was my base peak because it was the tallest, so I'm just going to add that label there. So my mass spec's done, IR is done, hydrogen NMR, carbon NMR. What would be left with this to do is to actually draw in the structures. So I have those on my other page, so I can copy and paste those over. And then in our defense section, so this one has an ester in it. So I'm going to go back so I can see the structure here as I write my defense. I'm just going to kind of do bullet points here just to kind of give you an idea of what I would expect. So we could say that we know that it had an ethyl because of the triplet and quartet pattern in the NMR. And we know that it had an ester because there was a singlet in the carbon NMR, so we knew that there had to have been a carbon without hydrogens, and the peak at 1730 in the IR, and we knew that there had to have been a methyl isolated from the rest of the molecule because of the singlet in the NMR. And then that kind of tells us what all the puzzle pieces are. And then putting those puzzle pieces together, we knew that the oxygen was next to the ethyl because the CH2 had a high chemical shift. And really we could say had the highest chemical shift. So the defense is essentially saying, here's how I figured out all the puzzle pieces, and here's how I know they went together in that way. If you have a little bit tricky of a structure, or you're just not sure you put enough in, I could always put that I knew it wasn't the other option because the oxygen, I knew the oxygen couldn't be next to that single methyl because the shift value for that methyl wasn't high enough. So it just kind of gives you a little bit of information. You could do bullet points, make sure that they're clear and concise. I wrote mine very fast, so they probably weren't as clear as they should be. You're going to put your structure on here twice though, so I'm going to copy and paste mine. Copy. actually haven't done this from my, I don't think it copied. Alright, so I haven't done this from my little whiteboard thing, so I don't know if it's going to work into Word. I don't think it is. I think I have to play around with it a little bit more. But you would either copy and paste your structure over with labels, and usually people put that in, next to the tables, and then you're going to copy and paste it again down here without any labels, just to make it nice and clear. Okay, so let's switch gears and look at the other unknown. So this is unknown 46. It actually has a typo in it because it doesn't actually have the number up there, but it is unknown 36, or excuse me, 46. Let me write that up there so I don't say it wrong again. And I have a blank test page over here, so I'm going to put 46 right there. And we're going to do the same first step. We're going to start by figuring out our chemical formula using, oops, that is not what I wanted to do. I just want to zoom in on everything. There we go. So we have carbon at 54.90, hydrogen 4.61, nitrogen 9.15, oxygen 31.34. So we're going to do the same steps. That first step is dividing by the molar masses. So I get 4.57, 4.56, 0.65, and 1.96. Alright, now we're going to divide them all by the smallest, which is the nitrogen value, the 0.65. And we get 7, 7, 1, and 3. So my empirical formula is carbon 7, hydrogen 7, nitrogen 3. And we're going to check that against our other data. So our mass on our mass spec says 153. And the molar mass of this, if we add it up real quick, so 7 carbons and 7 hydrogens and a nitrogen and 3 oxygens is 153. So this is my empirical and molecular formula. Okay, so I'm going to start with, actually let's start with our degrees of unsaturation. So 2 times the number of carbons plus 2 plus 1 for that nitrogen minus 7 all over 2. 14, 15, 16, so 17 minus 7 over 2. So we get 5. 5 degrees of unsaturation. So that does seem like a lot, but it at least tells us that we are dealing with a compound with lots of pi bonds or rings. And when we go look at our NMR, we can see that we have a peak at 6.9 and 8. So already we know we have a benzene ring. So that already takes care of 6 of our carbons. Notice that the integration here is 2 and 2. So that tells me that I have 2 substituents coming off of my benzene ring. So this is going to be C6H4 because there's 2 things coming off of there. So that also tells me that I have one more carbon to be accounted for. But this 3 right there, that's going to be a methyl group coming off of our ring. And so all of my carbons are accounted for, all 7 of them, and all 7 hydrogens. And so then that means we're left with the nitrogen and the 3 oxygens to assign. So let's go back to our table. There we go. So in my hydrogen section, hydrogen NMR, I would say that that peak is at 3.8. It is a singlet and it contains 3 hydrogens. The next peak is at 6.9. It tells us, that makes it nice and easy. I would call this a multiplet. It looks like it's probably like a doublet of triplets, but it's just not clear. So I'm going to call it a multiplet. There's 2 hydrogens. And then again at 8.0, another multiplet and another 2 hydrogens. And then while we're here, we're going to look at that carbon data. So we have 168.1 singlet, 140.7 singlet, 124.6 doublet. Whoops. Let's try that again. Tab, doublet. There we go. And 115.0 doublet and 56.0 quartet. This also matches nicely with what we already know about our structure. So any of the carbons in the ring that have a hydrogen attached to them are going to be doublets. The hydrogens that just have some kind of substituent on them don't have any hydrogens, so those would be singlets. This is our quartet. Now, here's another piece of information we can see from our data so far. In our carbon NMR data, there are 2 singlets and 2 doublets. So there's only 5 unique carbon peaks. That tells me that there has to be some symmetry within my structure because we know we have 7 carbons. Also, the shape of my NMR right here, the fact that our hydrogen NMRs are broken up into 2 environments, tells me about the substitution on my benzene ring. It tells me that it has to be para-substituted. So we don't know what's attached right here and right here, but we know it's going to be para-substituted because these 2 hydrogens are going to be in the same environment, and these 2 hydrogens are going to be in the same environment. And then these carbons are the same environment, which would give us one of the doublets. Those carbons are in the same environment, which would give us the other doublet. So that accounts for our hydrogen information and our carbon information. So we still don't know what to do with the nitrogen and the oxygens though. So we're going to go look at the IR, which gives us a lot of information about functional groups and the heteroatoms that we might have. So when we look at the IR for this, I'm going to start on the left and work my way across. And we definitely have a small peak right around 3100. I'm even going to label it as weak. This is sp2 carbon hydrogens. So these are the carbon hydrogens within that benzene ring. And then again, there's a peak right below that. So at 2900, 2800, again, they are both weak peaks. And these are sp3 carbon hydrogens. So that information tells me that I have a benzene ring because I have carbon hydrogens on those sp2 carbons, but I have some other type of carbon hydrogen as well. And then a little bit farther down the line, we have a peak right here at about 1600, and because we know we have a benzene, another peak we can look for is this one right here at 1475. So those two peaks are telling us that we have carbon-carbon double bonds, but specifically aromatic. There's a peak, let's see, which other ones were we going to label? Oh, we do also have this strong peak right here, so right above 1500, so about 1550, and then a pretty strong peak right here as well. Now I am going below 1500, but we do need some more information to help us analyze this, and so that peak at 1550 and then at 1350, these are both pretty strong, sharp peaks, so I'm going to label those. And if I look on my table for my IR, this tells me that it belongs to a nitro group or an NO2 group. So this helps also explain where the nitrogen and two of those oxygens are coming from. And then one more peak that's pretty strong is the next one over, so right here at 1300. And this is a pretty common one to see. A peak at 1300 is a carbon-oxygen single bond. So with this new piece of information, we go down to our structure. We knew that we had a methyl group. We just didn't quite know how it was attached. But now it makes sense that we would have a methoxy group and a nitro group. So that kind of brings our whole structure into play. We have an NO2, we have a methoxy group. I'm going to label my carbons A. I'm going to label these both as B because they are equivalent to each other. C, D, E. And then on my table over here, that singlet we know is the methyl group. It's 3 hydrogens. Now for the benzene hydrogens, this one can be a little bit trickier, but the one that's closer to the electronegative group will have a higher number, and the nitro group is actually more electronegative just because it has so many electronegative atoms. And so that, oh, but I did that backwards, didn't I? See? B, there we go. And then for our carbon data, I'm going to start down here at the easy one. The quartet would be E. The singlets, A and D are my singlets. They're the ones without any hydrogens attached to them. A is going to be a little bit higher because it's attached to the nitrogen and 2 oxygens. So a big electronegative group. And then same thing with our doublets. So the doublets would be B and C, and B is going to be a little bit higher than C because of that nitro group. So again, IR, hydrogen NMR, and carbon NMR tables are done. So we're going to go back and look at that mass spec. So that first peak is at 153, and this is my molecular ion peak, so I'm just going to label it with a capital M. The next peak, 123. 153 minus 123 is 30. The next peak is 92, so this is M minus 61. And then the last one is 77, which is M minus 76. The 153 is also my base peak, so I'm going to put that right here. And then that molecular ion, we can just label it like that. So that just means we have a couple left to label. The 30, when we lose, for this structure, when we lose 30, that is going to be our methoxy group that's leaving. So I'm going to write this as OCH2. This actually would leave behind a hydrogen. And so what we're left with is our benzene ring and that nitro group. A way to abbreviate a benzene ring is a pH. So I'm going to write it as pH or phenyl. NO2 is what's left behind. And then we have the 61 that it gets lost. So our the 61 that gets lost, I think that the 61 that is lost would be a combination of the methyl from one side and the NO2 on the other side. So it's breaking off in both locations. So the oxygen is staying behind. So what stays behind would be this, and what breaks off would be our NO2 group and our methyl group. There we go. And then that last one, this is actually a really common fragment to see for benzene rings. So let me go find a picture for us. So it's called a tropylium cation, and it's a very common fragment to see with benzene rings. And so the peak that we're seeing there at 77, actually nope, that doesn't work out math-wise. So let's see, 6 times 12, 72, plus 5 would be 77. So really what's left behind here is just the benzene ring. And the NO2 and methoxy have broken off. With this one, or with really any of the mass specs, if you're off by 1 or even 2, it's not a big deal, because what we're looking at is how these are breaking, and so there can be some rearrangement that occurs in order to make a cation more stable, and as the hydrogens move around, it's obviously going to change the mass. So mass spec's done, IR's done, hydrogen NMR, carbon NMR. I'm going to scroll here so we can see our structure. There's our final structure. So again, I would copy and paste my structure in with the labels, copy and paste it without the labels, fill in the formula, fill in the mass. My defense for this one, so we know it was benzene because we had peaks in the NMR between 7 and 8. We knew that it was para-substituted because of the symmetry in the carbon and hydrogen NMR. We knew that it was an NO2 group because of the 1550 and 1350 peaks in the IR, and it's a methoxy because of the oxygen carbon stretch in IR and the peak in and the peak in the NMR at 3.8. So this actually kind of puts everything together. So we know we have the benzene ring because of the NMR. We know why we have the NO2 and the methoxy, and then we know that it's para-substituted because of the symmetry, and I'm even going to add here, and because there are only 4 benzene hydrogens. So that tells us that we know it's di-substituted, and then we know it's para-substituted because of where they're at. So resources on how to approach this. Grabbing my lab book here. The techniques section in your lab book is definitely going to be your best friend for this. Technique 25 is the IR. Technique 26 is the proton NMR, and Technique 27 is the carbon NMR. And Technique 27 is definitely not going to be incredibly useful, but the IR one is very helpful, as well as the hydrogen NMR one, and I would suggest checking out the IR one. One of the things I had mentioned is this little table that's on the bottom here. It tells you all of the different types of carbonyls and where we would expect to see them. We know that we normally get a carbonyl peak between 1600 and 1700, but this gives you good specifics. The other good table that's in here is the information about benzene rings. So I'm on page 902. These two tables right here are showing you what type of peaks you would see. I know that didn't actually focus on it, but it's showing you the types of peaks you would expect to see for all of the different substitution patterns in a benzene ring. So it's giving you a ton of information. So for the IR, I highly suggest start looking at page 899, and it walks you through all of the different types of functional groups and how you would see them in the NMR. Or excuse me, in the IR. Sorry, I flipped to the NMR section in my book here. And then for the NMR, it goes through some good examples in the lab textbook, but I think that your lecture textbook is just as helpful. So hopefully that will get you started and give you enough information. You know, you can always email me and text me if you need more guidance, but that is it for this video. Thank you.